Well, the good thing of this presentation is that we really care for showing you all the relations we set up, and then to hear some opinion about that. Okay, please.
Okay, this is what I immediately say. So my point now is to give you the main ingredients of the framework, the mathematical framework. I said there are no specified equation, but just relations in order to set up the main ingredients of what we would like to model. We begin with a population of what we call agents with a number NT of agents and a set of resources in the environment. And we first start by setting what we call a physiology. A physiology in this sense is an algorithm that defines the resource management behavior of the agent. That means defines what the agent is, how it relates with the environment. In particular, 4 main points. First of all, the resources that the agent needed in order to survive. No less than the amount of resources, otherwise she dies. And then the efficiency in the extraction and the use of these resources. These 3 elements create what we call the resource intake target. So what the agent would like at maximum to extract for the environment. What is his target for extracting resources from the environment? So we call physiology, that is the characteristic of this agent, a set of the amount of resources he needs to survive, some efficiency parameters, and what he would like to take from the environment. What do we mean by environment? Since our observation is the agent, the environment is all the elements of the world and of the population that are not part of the agent. So we define as environment the resources that are available at the population level, so RT, the number of agents, and all the other physiologies that he observes. So for me, for an agent, the environment is all the resources and all the characteristics of all the other agents. Once we set up the environment and the physiology, we can go and see what is the extraction mechanism of resources from the environment. First of all, we have a constraint such that the amount of resources that are extracted for environment cannot be larger than the total resources available in the environment. And then there is a kind of game among all the agents in the population. There are the resource intake targets of every agent, but for sure it cannot be taken for granted that every agent extracts the maximum amount of resources he wanted. It can be a fight, it can be cooperation. What in economics we study in game theory, basically, is how in a society agents manage to extract resources to decide together. This can be conflictual, cooperative, and so in these resource extraction mechanisms, you can have an whole set of mechanisms that can describe different societies. You can have warfare, or you can have labor, division of labors. This is our economist examples, and he can provide you different examples. For sure, every agent has to extract at least the minimum amount of resources he needed in order to survive. Then, once we set up the static part of the framework, it means the environment, the physiology of the agent, and how they extract resources, we start to go into the dynamic part. First of all, agents have to reproduce. In order to do that, we consider sexual reproduction. So we imagine some matching function. This can take into account different possibilities. Since we have physiologists, that means what other agents, what I see of the other agents, matching function can depend on the physiologies of other agents. There can be some kind of assortative mating, that means that agents with similar similar physiology match with others, or on the opposite, that different physiologies tend to match with each others. In a way, physiologies matters because they don't only make agents extract resources, but they care in the sense they influence their offspring, the number of offspring they have. In particular, each agent selects, depending on the matching is inside, the number of the amount of resources to take for his own survival and how much to invest for offspring cares. And thus, we set up a function saying that the number of offspring of a given matching actually depends on the resources that each agent extracts and on the decision, the shares that each agent takes of resources for himself and for offspring. That means that the number of offspring at the end depends on the physiologies, depends on the characteristics of the agents. In this sense, in the dynamic part of the model, we have the resources of the matching, and depending on how the matching function is expressed, different matching can have for sure a different number of offspring, and so the physiologists can have different impact on the reproduction of the agents. Then we need to set up how resources reproduce in a way and regenerate. We can have a standard function of regeneration of resources in which resources generate with a parameter lambda, but if we want to consider some more complex cases of, for example, niche constructing cases, or what in economics we name in the same way some investment in order to reproduce resources in the environment, we can also take into account for endogeneity of the resource regeneration parameters with the action or with the choices of the different agents. In this sense, the resource regeneration process is also influenced by the physiologists, by the choices of the agents, and all the previous process we described. At the end, we needed to discuss a little bit how physiologists that are the driving force of this framework can be produced. We suppose the existence of a reaction norm, that is how the different agents in the society, in the population, can use or not use the information from the environment and from the other agents in order to form their own physiologies. What does it mean? That some reaction norms can display different levels of plasticity with respect to the environment. Some reaction norm may dictate just to use some social learning from the others, not take into account what the resources are. Depending on the problems, the problems that we are analyzing, different levels of plasticity may be displayed. More in details, we call X the reaction norm of the next generation, and in particular, this reaction norm, so how I form my physiology, may depend on the resources of the next period, meaning that, the resources on the period in which I live, mean that I can calibrate my physiology so that the amount of resources that I would like to ask to the society, depending on the resources that already exist. I can have some influence of the parental physiology. That means if there is some maternal cares or some transmitted values, depending on the problem we are analyzing, parental physiologies may actually play a role in offspring physiology. And also, there can be an aspect on all the other agents' physiologies. In some social science problems, these are the peer effects, for example. So actually, a reaction norm dictates how physiology is formed depending on environment, on other agents' physiologies. We suppose this reaction norm to be like a genome, so to be genetically transmitted from parents to offspring. That means that if the physiology is not plastic, for example, parents may transmit a reaction norm, say, please just do exactly this thing, this action. But the parents may also transmit a reaction norm that is very plastic, so that they teach their offspring to react very plastically to the environment. So in this sense, depending again on the problem, from my economic point of view, I can imagine some parents trying to transmit a progressist culture to the offspring, just say, okay, adapt very much to the environment, or a conservative one, just imitate what the parents do because this is correct. In this sense, the reaction norm exactly dictates how the offspring should react to the environment. We suppose for sure that being a sexual transmission, the physiology of the reaction norm of the offspring can either be inherited by the father or by the mother. In this way, we set up a closed model in which, depending on the reaction norm that is transmitted, every agent in the next period has a physiology, so can extract resources, can compete in the society for this extraction of resources. This is meshed with another agent, can reproduce. At the same time, there can be a niche constructing effect of the action of the agent. He will go into explain a little bit the relations between this and, sorry.
I don't think how much time do we have, but I would like to at least tell with words what is evolution in this strange framework we built. So evolution in our framework minimally consists in the cumulative change of the physiologies of the agents that compose the population, and in the fluctuation of their numbers, because they can be also influenced, the population size can be influenced. At each generation, physiologists develop according to a reaction norm that may or may not take into account the resources that are in the environment, in the physiologies of all the other agents of the population, and possibly also have a special influence from the physiologies of the parents. And parents are part of a generation that, like any generation, has differential mating and reproductive success. And they bias, the parents bias the offspring's biology, not only by giving them the reaction norm, but telling them to how biasing the final physiology which is produced. And additionally, also, evolution may also consist in the differential diffusion of different reaction norm in the population. So in any case, there is this population extracting resources from the environment, and also possibly niche constructing, that is, adding resources to the environment with its own proliferation. And so there is an additional positive feedback between the population growth and the resources in the environment, which are the same resources to which the physiologists, the reaction norms react to produce the physiologies, the phenotypes. So I just want to highlight where Fabrizio told about the economics, to highlight the concepts of biology that we tried to put here. So we want, for example, we want plastic agents. We want agents that produce the phenotype actively in reaction of stimuli. This is very useful for cultural evolution, but this is also very present in biology, as we know. For example, 5 minutes, lot of stuff. For example, I looked for some interesting examples, like the salamander's larvae that develop in a way or in another according to the phenotypes that are present in the population, or even a tree that grows in a way, develops a phenotype in presence of a crowded environment or of a very rare environment. So, and we want agents to be ecological agents, agents that stay in an environment and have a relationship with the resources that are there. We also want inheritance not to be an agent copying an agent, so an agent copying how the agent looks like, but an agent that copies the rules according to which it becomes what is it. So I'm copying from my parents, I'm copying the rule according to which I develop my physiology. I don't copy their physiology. And this opens also the space for influence, for the influence of the environment and of the resources. And then there is this matching and reproduction function, because it's true that with this framework we can we may build agent-based models that follow each agent, but we can also build probabilistic models where you derive from one generation, you derive probability distributions, and then you create the new generation, and you don't know which agent is son or daughter of whom. But it's important because through this influence of the parents to the offspring, we can model inheritance. Because one of the problems of these phenotypical models, and Marcus Feldman told us that it's not evolution because there's no inheritance, there's no genetics, there's nothing lasting that stays. And so you can, in this influence that the parents have on the offspring physiology, you can also include epigenetic inheritance or additional genetic inheritance, because other genes, extra genes, to which the reaction norm is sensitive. I could speak for hours about this, but maybe Fabrizio wants to tell us what can we study with mathematical models about.
I think that the next, we were imagining about how to first apply the next step, in the next steps, this framework. Since our key ingredient here is the reaction norm that say how an agent reacts to the environment, the first thing we can do is to study fixing one reaction norm, to study how changing the other ingredients of the framework may have an impact on the dynamics of the population. So we don't really at first study the selection problem of different reaction norm, but see how the changing in physiology, changing on the efficiency parameter, on the matching function, or other stuff in the model may change the dynamics of the population. And at the same time, compare different reaction norms. So we were imagining some reaction norm that change in the forward-lookingness. I mean, I can have a reaction norm that say, take as much resources as you can, or take care of your offspring, so maybe don't waste everything in the next period. So see how different this reaction norm may be in terms of dynamics of population, so extinction or survival of the population, just an ecological setting. But then we can set up also a model in which we have reaction norms compete. So then here we can analyze a selection problem among different norms, in which we have matings among agents with different reaction norms, with different physiologies. So and see how plasticity of reaction norm may be important in different settings depending on the other ingredients of the model, and if especially there are some necessary features in the reaction norm setting in order to make these norms survive in the long run. So analyzing actually how the selection pressures act on these reaction norms, and especially see what are the ingredients that we really think are necessary in order to see a reaction norm to survive in the long run. I know. Okay, I'm finished. Sorry.
Thank
okay.
You.